Okay, so in this, the 11th lecture, we will talk a little bit more in detail about DC particle accelerators. By DC, of course, we mean beams that are coming continuously in time, and this is roughly the way we will go about it. The need for DC accelerators, then we will talk about three kinds of Van de Graaff machines: single-ended, tandem, and the folded tandem. Then some of the additional devices or systems that we have, so-called add-ons or auxiliary things, which actually enhance the capability of the accelerators, namely the beam pulsing system, uh, and of course neutron time of flight. There's a typo here, so this should have been neutron time of flight facility. Okay. Then we will talk about the Linac booster to increase the beam energy, and then I will summarize. Okay, so in lecture 3 we had already discussed very briefly DC accelerators, cascade generator, Van de Graaff. They were introduced briefly. So we will go over some of that quickly, but also discuss in a little more detail some of these aspects. So the need for accelerators in general, including DC machines, is that you need to overcome the Coulomb barrier. So when you have nuclear collisions, you have positive charge on both the projectile and the target, and you need to overcome that Coulomb barrier and get the each of the projectile targets to see the nuclear forces in order to have nuclear reactions. So it is also necessary to create new particles. So the center of mass energy has to be greater than the projectile, than the, let's say, the mass of the particle that you want to create. You also need accelerators for, in general, of course, to produce synchrotron radiation, free electron lasers, spallation neutrons, secondary beams of pions, muons, kaons, neutrinos, and so on. So what is shown in red is things that can be done with DC machines, and of course the other ones need higher energies typically, and they need a RF acceleration. So RF machines. So DC machines are often used for light and heavy ion reactions in the energy range of about 5 to 10 MeV per nucleon. There are several applications where again DC machines are used. So in general, of course, isotope production, electrons, protons for cancer treatment, etc. But DC machines are particularly useful for accelerator mass spectrometry for carbon 14, chlorine 36, 10 beryllium, 85 krypton dating, and so on. And also for the surface and bulk treatment of materials, impurity estimation by Rutherford backscattering, measure nuclear resonances, where, by the way, these DC machines have a particular advantage because you can make beams with a very narrow spread in energy, which is not so for the, in general, for RF machines. Of course, you can do special things in order to make that the energy width narrower, but still you can't achieve the kind of energy width that you get from some of the DC machines. So let's discuss a little more in detail than we did in lecture 3, the Van de Graaff single-headed machine. It of course consists of a high voltage terminal, which is at a positive voltage, and you have a positive ion source sitting inside that high voltage terminal. Then you have an accelerating tube. You have electrostatic or magnetic quadrupoles to focus the beam. Then you have an analyzing magnet to select the momentum by charge of the accelerated ion. Then a beam transport system, which includes X and Y dipole magnets. In other words, the beam can be deflected in the X or in the Y direction. If you say that Z is the direction of the beam, then these magnetic dipoles can be made to pass through the center of your beam pipes or slits or collimators, if any. Then there are quadrupoles to focus these beams, both in the X and Y direction. There are beam profile monitors, which define the intensity profile of this beam in X and Y directions in 2 dimensions, cross section. And then there are Faraday cups which measure the overall beam current at various places. So in case you lose beam, then you have to tune the transport elements, which includes, as I said, the steerers and quadrupoles and so on. The high voltage dome, of course, is in a pressure vessel, with an insulating gas, and the best insulating gas that we know of for such purposes is sulfur hexafluoride, SF6. This gas has a large affinity for electrons. So if there is any ionization produced which could possibly lead to multiplication in the high electric field near the dome, then that is prevented because these electrons quickly get attached to the SF6 molecule. And this way you can achieve singulated machines where maximum terminal voltage is of the order of 5 to 12 MV, million volts, and such machines have actually been used in the past and even presently when that is the way to go. The positive ion source in the high voltage terminal usually sits at about 5 to 20 kilovolts plus. So that is the positive ions acquire that. If it is singly charged, it acquires an energy between 5 and 20 kilo electron volts. Usually these ion sources of the RF type, where the RF energy is coupled into the plasma, and that's how you produce ions. So lots of these RF photons are actually absorbed and so on. Or you also, some of these machines even have so-called pig sources. But most of the newer machines have ECR sources, electron cyclotron resonance sources, which can give a very high current output. The tandem Van de Graaff is of course an idea that has also been around for quite some time, and that consists of a high voltage terminal with accelerating tubes on either side. So you have to inject negative ions. You have the terminal at a high voltage, you inject and select the right mass ion through magnetic dipole, then you inject it into the accelerating tube, and then once it comes into the high voltage terminal, you strip it of one or more electrons depending on the particular ion that you are having. If you have protons, of course, there is only two electrons to be stripped from the H minus ion. But if it is a heavier ion like say silicon or something, you can, depending on the voltage, let's say of the order of 12 million volts, you can strip up to 9 or 10 electrons. The stripper is, for light ions is usually a carbon foil stripper. But you can also have a gas stripper, which is good for heavy ions, because carbon foils, because of the large d by dx for heavier ions, they break, and you have to. So there is an assembly there which you can bring a good foil into the beam direction, into the beam path. But this becomes inefficient if you have a very heavy ion like say heavier than silicon, sulfur, titanium, or nickel. And so in those cases, you actually use a gas stripper, because a gas stripper, there's no problem of a foil breaking. And then that you produce a plus Q charge state, which is then accelerated to a total energy of Q plus 1 times the terminal voltage. The 14 MV pelletron, for instance, delivers beams of protons. This should actually be helium. Okay, it should be a helium alpha particle, or a helium 4 ion, and 6, 7 lithium, up to about 58 nickel at beam currents of a few particle to 100 particle nanoamperes. Other beamline components are similar. The steerer, quadrupoles, beam profile monitors, and Faraday cups are similar to that which are present in a single-ended Van de Graaff facility. The vacuum in all these beam pipes, including the single-ended machine and even the folded tandem, the typical vacuum in these beam pipes is about 10 to the minus 7 millibar. For reference, the atmospheric pressure is 1 bar, which means 10 to the power of 3 millibar. So it's 10 to the power of 10 times smaller than atmospheric pressure. The tank pressure of the SF6 is about 5 to 6 bar, which means 5 to 6 atmospheres. So it's about 80 psi or so. The voltage stabilization, so since these are DC machines and they have a particular advantage to where the beam energy is known very precisely, this is done by a so-called vertical slit current pickup post the analyzing magnet. So the analyzing, as the beam comes down, the analyzing magnet bends it by 90 degrees, and the high energy beam falls on the lower vertical slit. The low energy part of the beam falls on the upper slit. So it's a very fine beam, usually of about a couple of millimeters. So some of the current is picked up by the vertical slits up and down, and then depending on whether the beam energy is somewhat higher, then you can stabilize that by actually taking this pickup and giving a negative feedback to the charging system. Okay. There is also another generating voltmeter which is near the high voltage terminal. That is a capacitive kind of pickup. There is a rotating set of blades which are insulated, and you can pick up the voltage on that, and that is another way of stabilizing the voltage. So you can stabilize this voltage typically at 14 MV of the order of plus minus 3 kilo electron volts. Perhaps it can be done even better if if you do things better. The beam diagnosis, as I said already, is done by XY beam profile monitors and Faraday cups. So this is a picture taken from inside the pelletron vessel at pelletron pressure tank at TIFR, the PLF facility at TIFR Mumbai. And this is a section, one of these sections of these accelerating columns. So you have this accelerating tube here, and then there are posts here which support this thing. So it is so that this is right from the bottom. This whole thing is supported. Okay, so then you have also so these act as insulators, come strong supports. The whole structure would be several tons, and you also have a so-called rotating shaft, which is made of perspex, which can transmit mechanical power to something in the terminal, because you require power there also. So there is a generator there which provides the power locally. So coming to these various elements that are there, like the bending magnets, steerers, switchers and analyzers. So of course, you can have these at low energies. You can use electrostatic steerers and electrostatic quadrupoles, which can deflect and focus the beam depending on the energy, kinetic energy by Q of the ion. And this is in fact done in the low energy end of the tandem accelerator. The advantage is that you can, once you select a certain mass, then you don't have to actually change the settings of the electrostatic steerer. Okay. So they are independent of the ion the mass that you are selecting. It only depends on the voltage, because T is just given by -1 times the voltage. So it just depends on the voltage. Okay. And you can select the different masses using the magnet, but the electrostatic quadrupoles and steerers, their voltages are independent of what mass you are selecting. Then there are the magnetic steerers and quadrupoles, which deflect, focus the beam depending on the momentum by charge. So the 90-degree magnet, for instance, that is above the low energy part of the machine, it selects ions of a particular mass from the ion source. So the B field is, as I said, just proportional to m by q square root. The analyzing magnet, which is below the high energy end, selects the P by Q of the accelerated species. So some pictures of the XY steerer magnet are shown here. So using this module, you can actually move the beam in the X and Y directions. The ion beam can be moved in these two planes. And this is the analyzing magnet. It so happens that in the PLF facility at Mumbai, you have a dual analyzing magnet. So there are two arms to this. So there is a switcher above this, a 20-degree switcher, which switches it to this part or to that part. This part goes to an old beam hall called the cascade hall, and this part goes to the new hall where you have the Linac boosters. So of course, this is particular to the machine that we have at the TIFR Mumbai facility. This is the picture of the switching magnet there. So the beam comes in here, and then this switcher can actually switch the beam to -30, -15, 0 degree. 0 degree of course means no current in the switching magnet, +15, +30 degrees and so on. So you can have beam lines, and this switching magnet can switch the beam from one beam line to the other. As I said, the quadrupole magnets focus the beams. So here is an example of the field, how it changes in a magnetic quadrupole, and the force is felt by the charged particle as it moves. So the particle is moving into the figure, and this is these are the field lines here, B are shown here, and these are the forces felt by the charged particle as it moves into the page. This is just a cross section shown. So you can see that in the vertical direction you have a focusing effect on the beam, and the horizontal direction you have a defocusing effect. Okay, so any such quadrupole, and you can show that very easily using Maxwell's equations, that they cannot focus in both directions. Okay. So what is done is that you have a quadrupole device which focuses in the x direction, you have another quadrupole which focuses in the y direction, and if you put two such lenses, if you remember your optics, then if you put two such lenses, you can arrange it such that you have overall focusing in both the x and y directions. As I said already, above the low energy part, we have the electrostatic devices, because they are very easy to run. They are very low current, high voltage power supplies that are needed to operate this. And again, a similar principle operates here, that you have these electrodes and you have focusing in one direction. So you have a positive, if you have a negative ion, then it gets focused in the x direction and defocused in the y direction. Again, if you have two such lenses, you get overall focusing. This is a picture of the magnetic quadrupole at the Pelletron Linac facility. So, what is done at the Pelletron Linac, and this is probably done elsewhere as well, is you split one of these quadrupoles into two parts. So, you have a more symmetric design. So, let's say you have a x quadrupole in the middle, and you have the y quadrupoles, half of these y quadrupoles in this. So, it mimics MQX, but because it's symmetric, the aberrations are somewhat less. So, both of them nicely focus at a spot that you can decide by tuning the currents. These are pictures of a beam profile monitor. The beam profile monitor is a semi-helical wire which is rotating using this motor in vacuum. Okay. So, there is a coupling of the rotary motion to this helical wire, and by a careful design of this, which is at roughly 45 degrees to the beam, then in half cycle you actually scan the Y beam profile, intensity profile, and in the other half of the scan you actually scan the X profile. So, this is the output which you get. There are preamplifiers there and so on, and so this is in the Y scan and this is the X scan. So, this is when you have focused the beam very well on the beam profile monitor, and the full width of course can be seen. You do not see the calibrations here, but you can see that in terms of millimeters. So, usually these things are focused to about a couple of millimeters, 1 to 2 millimeters, and the intensity, the height of this peak tells you the intensity of the beam, that is proportional to the intensity of the beam. And so, this is an example of a Faraday cup. So, this is a cup which can be put in when you want to measure the current, and you can pull it out using this device here. Of course, this is always in vacuum. So, you have something which is it can pull this thing in and out of the beam. So, when you want to measure it, you put it in the beam, you stop the beam, and then you want it to take it downstream of this, you pull it out. So, this is a layout of the 14 million volt Pelletron accelerator at the PLF facility at TIFR Mumbai. This is a line diagram. So, you have the negative ion source, it gets bent here. Then I will talk about this add-on device called the buncher, that is here. This is the buncher, and then it passes through the accelerator, it gets stripped, and then the positive ions get bent by this two-way analyzing magnet. So, if you want to go here, then this beam is bent, it falls on a pair of slits, and the vertical slits are used for beam energy stabilization, and the horizontal ones are actually used for a very different function. Once you bunch the beam, there is also a so-called DC current in between the beam bunches, and that can be cleaned up by applying a RF voltage whose frequency is half of the bunching frequency, and then that DC beam can be made to completely disappear. So, the RF phase can be arranged such that the beam bunch does not see any voltage, but at other times you see a voltage and it either goes to the left or the right slit. And then of course, the beam goes on downstream into your target area, where the experimenter has his own target chamber, detectors and so on, and you do the experiment. This is an example of the folded tandem. There are several in the world. The one which is there in Mumbai is called the Fotia accelerator for the folded tandem. It's a 6 million volt machine. So, in the old 5.5 million volt single-ended Van de Graaff, things were modified to put two accelerating tubes, a 180-degree analyzing magnet. So you have a negative ion source putting in a beam in the low energy end, then you have a stripper, and then this positive ions bend by 180 degrees, come down, again get accelerated, and then there is an analyzing magnet which sends it to the experimental hall. So I will now talk about some of the enhancement of tandem accelerators and beams and so on. So one is of course the beam pulsing system, which I have already mentioned. Uh, in the Pelletron, we use a double drift buncher, which is just above the low energy end, and basically it bunches the DC beam with a repetition rate of roughly 9.4 megahertz. Uh, and you can ultimately get a beam width at the output of the accelerator of about 2 nanoseconds width, full width at half maximum. Uh, Two RF frequencies are applied to two cavities, F and 2F, and then these two cavities obviously have to be they are separated by a certain distance. That actually mimics the applying of a 3F frequency, and this sort of mimics the ideal voltage RF profile that you would need, namely a ramp voltage, so that the particles that come earlier with respect to a phase of 0, let's say in the middle of a certain window, then the early ones get decelerated and the later ones gets accelerated, and so this these F and 2F separated actually mimic this ideal ramp voltage, and this produces a bunch beam, but you also have DC beam in between. So that we will see in the next slide. Namely, you have a beam here which is bunched, but then you have also tails of this, and so this is the beam that I should have probably had a better figure. We have two bunches, uh, and then you throw out the beam in between. But in any case, you can see that there is this beam here which can be cleaned up by the so-called sweeper that I mentioned, that only the central part sees no voltage and the rest of it sees either a positive or a negative RF voltage and gets swept out. So this is a uh, beam 70 MeV oxygen 16 beam without and with the sweeper. There is also something called the beam chopper, which can take one bunch out of 2 or one bunch out of 4, 8 or 16 bunches, and so that you can do measurements involving long-lived isomers, because as I said, the primary frequency is 9.375 megahertz, so roughly 107 nanosecond between two beam bursts. But if you require a longer cool time in order to study delayed gamma rays and stuff like that, then of course you can throw out some of the bunches and you can have a beam chopper which does that job. This is the paper that from where these figures are taken. This is just to show you some of the largest tandem accelerators that are existing in the world. All of these three no longer exist because they have been dismantled or they are used for other purposes. And for instance, this is the 20 MV tandem accelerator at Daresbury. This was used for nuclear physics, but I think it is now being used for other purposes, not for nuclear physics. There was the Vivitron, which worked for a while. It was supposed to be the highest voltage tandem accelerator, and this was designed for going all the way up to 35 million volts. In practice, because of various problems, including one with that there is a horizontal machine, it only reached 20 million volts. And eventually, some experiments were of course carried out with the Vivitron at these lower voltages, but then eventually it was shut down in 2003. Uh, Another very successful folded tandem accelerator, this was built by the National Electrostatic Corporation, was the 25 million volt machine at the Oak Ridge National Laboratory in the US. So without the accelerating tube, it reached 32 million volts, but with beams, it was used regularly up to a terminal voltage of 24 million electron volts. So it also did some radioactive ion beam experiments. The final thing that I want to talk about is how to increase the energy of the tandem machines, the beams from tandem machines. So, again, this has been around. There have been several devices that do that. All over Europe, there was a device that used a room temperature booster. Then in Seattle and Stony Brook, they had these superconducting Linac boosters, and in Argonne National Lab also they had a superconducting Linac booster based on a different technology, not a copper plus lead coating technology. They had used niobium superconducting cavities. So, the one in Mumbai at TIFR, that Linac booster is based on the quarter wave resonator, uh, which is based on a copper conductor which is plated by lead, and when you take it down to liquid helium temperatures, then the lead becomes superconducting. So, the advantage of superconductivity is of course that you require less RF power. Uh, this of course operates at 150 megahertz. So, these cavities resonate at 150 megahertz nominally. And this is a picture of the beam line, the Linac booster beam line. I showed you that analyzing magnet, that two-way analyzing magnet. So, one of the ways goes into the Linac hall. So, you have a super buncher which takes it from 2 nanoseconds to a few hundred picoseconds, and then it goes into the Linac booster. There are two arms because of the constraint of space. So, there are three cryogenic modules here, each of which house 4 resonators each, and then there is a section here which has 4 cryostats. So, in all you have about 28 cavities, superconducting cavities, and this is a picture of uh, the area in the in the pre-bend portion, and this is the post-bend portion. So, there are 7 big cryostats in all. This is the basic entity which accelerates particles. This is a cutout view of the so-called quarter wave resonator. So, it is these two gaps where the RF is applied and the beams are accelerated. So, this is designed for a particular velocity, about 10% of the, I think 5% of the velocity of light. But other velocity particles can also get accelerated with less efficiency. Uh, This is a quarter wave resonator photo taken from the bottom. So, you can see the copper shining here, and then this is plated with lead. This is a view of the cryostat which has 4 of these quarter wave resonators. So, there is the helium tank which cools this and makes the lead go superconducting. There is this chamber which you have to have vacuum in the chamber, and of course, you pump in RF power through the same way, through the same pipes. Okay, so this is as far as the accelerator goes. I should say that the Linac booster at TFR roughly doubles the energy that you can get from just the tandem accelerator, and it can take ions right up to nickel, such that you can make nickel plus the heavier targets in the mass 200 region to make nuclear reactions. If you didn't have the Linac booster, you could only make nuclear reactions for lighter ions up to about aluminum or even somewhat lighter than that. This is a list of the Nobel Prizes just to show you that accelerator building is a very important part of physics experiments, nuclear and particle physics experiments. You realize that right from the discharge tube, which is also actually an accelerator, to Simon van der Meer, who invented stochastic cooling for making the PP bar collider. So, these are the people who have got Nobel Prizes to various kinds of accelerators. This is the cyclotron, the Cockcroft-Walton machine, then the synchrotron, and so on. Okay, so in summary, we saw in some more detail the working of Van de Graaff type of accelerators, 3 types, and common to all of these 3 are the beam manipulation devices, the bending magnets, focusing quadrupoles, and the beam buncher. To enlarge the range of tandem accelerator for heavy ion reactions and to overcome the Coulomb barrier for the heavier projectiles, Linac booster, which increases the energy of the heavy ion and then takes it to so that you can make reactions with the heaviest targets. Thank you.